x2, for example, and we can just do it. So, but we will do it, I mean, step by step, and I mean, in practice, it will be fine. Substitute those values. So I got a question also from, I mean, some people, they want error backpropagation. So I'm preparing it for next week. So next week, we will talk about the mathematics of backpropagation, if it is very important. We talked about logistic regression last time. We finished that part, decision boundary, and we went to this linearly inseparable data set when it's linearly inseparable. This data set, it's I generated it using a function called make circle, I guess. Correct? Yeah, it's no, it's for iris data set. But anyway, for this one, if you have linearly inseparable data set, what is the definition of linearly inseparable data set? In fact, it's a data set which cannot be separated by a straight line. So we call it linearly inseparable. So if you can draw a line here, so if you can draw a line, so for example, if we need to draw a line here, it will be impossible to find a line to separate the red cluster from the blue one, right? So in this case, we can just call it inseparable, right? We can call it inseparable. How can we solve it? This is a huge problem. One way for, so it looks simple, but one way for solving it is to try to extend it with higher order features. So if we can add higher order features, maybe we can find a simple model for separating it. Because sometimes if you have, we have here x1 and x2, for example, right? We have here x1 and x2, and we just plot the data in two-dimensional space. But maybe if we can add a new feature, which is x3, for example, and the x3 is x1 square plus x2 square, maybe it's x1 times x2. So it can show the interaction, or it can represent the interaction, or higher order feature. Maybe in this case, maybe the problem can be separated using a straight line or a plane, for example. So when we extended it, when we added one feature, higher order feature, x3, which is x1 square plus x2 square, and then when we plot this data set in three-dimensional space, we have here x1, we have here x2, we have here x3, right? When we plot the data in this way, we can see that we have enough gap between the two classes, and it should be possible to draw a plane or to find a plane which can be used for separating those two clusters into two different classes, for example. So this is one way for working it. Therefore, I mentioned that working with data is very important. We need to spend some time working with the data, visualizing it, try different combinations of features. I mean, this approach, when we add a new feature, in fact, we call it feature construction. So we call this technique, it's feature construction. So we need to construct a feature, a new feature. It could be a super feature, for example, which can help us to solve the problem. And we will take example later on. So this is very important. So when you have a data set like this one, we cannot use a perceptron here, right? We cannot use a perceptron, we cannot use a logistic regression, because imagine I have a logistic regression and I have two inputs, x1 and x2, right? So and we need to have a decision which is 1 and 0, for example. 1 for red and 0 for blue. It will be impossible to find a straight line because this model, it will generate, in fact, a straight line which is omega 1 x1 plus omega 2 x2 plus b equals 0. So just imagine we will get this straight line. This straight line, it cannot help us. In fact, if you change it omega values and the b values, it will be impossible to solve this problem. So we cannot solve this problem using a logistic regression. But of course, maybe you can solve it using a neural network, right? Feed-forward neural network, for example, because feed-forward neural network, it will try to generate very complex shape. It will try to generate complex decision boundary, which can be used for solving this problem. So when we did that, in fact, when we extended the feature with the higher order feature, which is x3, what happened? Now the straight line becomes omega 1 x1 plus omega 2 x2 plus omega 3 x3, because we added x3. But what is x3 in fact? x3, it's x1 square plus x2 square. So it's multiplied by omega 3 plus b equals 0. Imagine that omega 1 equals 0 and omega 2 equals 0. So the decision boundary will be this one. This one, in fact, imagine also omega 3 equal 1. If omega 3 equal 1, so this equation will be x1 square plus omega 2 square plus b equals 0. Or you can just say it's equal minus b. In fact, this equation, it is the equation of the circle. So if you can substitute values for x1 and x2, you can plot a circle here. And I have this example later on. So we will go to this example, very soon. So when you use higher order features, you try to simplify your, you are extracting, you are inventing a new feature. This feature may help you to simplify your model, because now, in fact, when we use the XSV, I can just use a perceptron. It will be okay. Now I can use a perceptron. So 2 inputs or 3 inputs, right? It could be x1, x2, and x3. And finally, we can find a line. This one will generate this line, right? Maybe by chance, maybe omega 1 will be 0, very small value. Omega 2 will be also very small value, and imagine omega 3 equal 1. So we will generate a circle, and this circle will help us to differentiate. I did this experiment. In fact, I will show it soon. So in fact, we will get something like this one. We will get a straight line in the middle, like this one. Sorry, a circle. We will get a circle like this one. All points which are located inside the circle will be classified as 1. All points which is outside the circle will be classified as 0. So in this case, we can generate, in fact, a very complex decision boundary using this simple trick. So if you have inseparable data set, you need to check first. You need to check different combinations of features. So some people can try. There are some algorithms, in fact, which do this for you, but it's optimization algorithms. So I need to try x1, x2, x1, x3, sorry, x1, x2 to include the interaction, x1 square, x1 cubed, x2 square, x2 cubed, x1 times x2 square. So we need to try different combinations, and finally you can select the best set which can help you to classify your problem. So when it's linearly inseparable data set, just wait a little bit and don't try to build your system directly, because maybe it will be a very complex system, and when it's complex, you need more data to train your model, or you need maybe your system will have higher capacity. Higher capacity means it's complex model. It has lots of weights, and when it has lots of weights, we need more data to train the system. Yes. So I did this logistic regression, I guess, for iris datasets, but I don't know why we have this logistic regression for iris example. You have this code, in fact, but I guess we did that last time. And you have this logistic regression iris in this GitHub. You can just go to this one and try to run it. It's a logistic regression for 4 inputs, I guess. Yes, I use the whole dataset in this example, right? So in fact, if we need to draw our logistic regression model, it will have 4 inputs, in fact, right? Because this data set, it has 4 features. If you can remember, it has the sepal length and width and beta length and width. So we have 4 inputs, and we have 3 classes. In fact, we have 3 classes. But remember here, if it is, it has 3 classes, and also I try to do it for the 3 classes. In fact, we try to do it for the 3 classes. So yes, so it can work. This logistic regression, if you have 3 classes, it can work for multi-classes. So I've been working here for multi-classes, and we so in multi-classes, in fact, we will have 3 models, one for each class. One for each class, and therefore those weights, if you look into those weights, those are the parameters or the weights. This one, it's omega. Those are the bias values, right? So the bias values, we have 1, 2, 3 values, correct? We have 3 values, which means we have 3 perceptrons, for example. So we will have 3, 1 for each cluster, and all inputs are connected to the 3. For the weights, it will be 3 times 4. So this vector, in fact, it's 3 times 4, because we have 3 perceptrons or neurons, for example, and 4 inputs. So it will be like this. So logistic regression, we can use it for multi-class classification. A perceptron also, we can do it for the same task. We can just use it for multi-class classification. This one, it's no binary classification, it's multi-class classification. Why? Because we have in the labels here, we have Setosa, we have Versicolor, we have Virginica. So in fact, we have 3 classes. Yes. Implementing logistic regression, I try to implement it, in fact, not using the sklearn function, but also I did it using, I implemented it by myself, I guess. And yes, if you want to implement it by yourself, so this is the steps. So we have our data set. So our data set consists of some input features and target feature, X and Y. X, it means an example, and this one, it's R to the power of n, in fact. So it could be it might has n features or 4 features or 5 features. This is our hypothesis. This is our activation function, and our hypothesis will be that I mean, this is the activation function. In fact, this is a decision line which we will get, right? And we can just say that I mean, the hypothesis will be like this one. So the output y, it will be, for example, 0 and 1. 1 when phi omega of x greater than or equal 0.5. This one, it's otherwise. So in fact, this is a threshold function. If you remember the plot, so if we can go back here, this one, this is the next step. This is our hypothesis here. So because the output from here will be phi of x, right? So this is the output from the activation function. We need to convert this output into a class. We need to make decision. So we can just say that because the output will be like this Gaussian function, right? So all values which are greater than 0.5 will be converted into 1. We can just say that it belongs to 1. Otherwise, it will be 0. So this is the hypothesis which we have here. So for iris classification, I mean, when it's yes, I just used also I used here three features for 2 classes. I just do for iris classification. I just do it for 3 inputs, 2 classes. I used the first 100 points, which means we have 2 classes, and we try. So those are the 2 classes, right? And we have 3 features, and we have feature 1 and feature. I'm plotting it in 2-dimensional space using feature 1 and feature 2. Yes, sorry, we have here only feature number 1 and feature number 3. Correct? So I'm selecting 2 features because iris data set we have 4 inputs. So we can just say it's x1, x2, x3, and x4, and we have here the output. The first 50 points, it's a class 0. The second 50, it's a class number 1, and the last 50, it's a class number 2, for example. So we have 3 classes. So we just selected the first 2 blocks, and we selected x1 and x3. We selected this one and this one for training our model. I'm plotting it in 2-dimensional space first. So we are plotting it in 2-dimensional space, feature 1 and feature 2. And after that, I used, in fact, I mean, this assignment, it's implementing logistic regression. Yeah, you need to implement it by yourself, for example. So I have been implementing it, and I used it for classifying this problem. Yes. So first, I plot the 2 classes with 2 features. And now this is my implementation. In fact, this is my implementation for logistic regression. In the logistic regression, I mean, we do it like a mini batch gradient, correct? So we do it for each batch. So this one, it's matrix multiplication or it's vector multiplication. This dot product we use here, dot product, right? And this is the steps for doing it. And at the end, we calculate the cost and mean value of the cost. So we return the mean value of the cost, right? And we use this value for adjusting our weights. So finally, we can have this line. So now we can solve, I mean, the problem, and we can generate this decision boundary or the decision line. And this is how the error looks like. So we started from some point. It could go up and it could go down again. So it fluctuates. And finally, we can reach, I mean, it can converge maybe at 15, for example, after 15 epoch. Yes. I don't know if we talked last time about confusion matrix or not, but I mean, in machine learning, when you are building a model, there is a pipeline which we need to follow. First, we need to collect the data. We need to visualize the data. We need to use some pre-processing techniques, for example, to normalize your data or to standardize your data, for example. Now we are ready to, and also feature selection and feature engineering. So maybe it's similar to this circles. maybe X1 and X2 is not enough. I need to generate new feature. We need to construct a new feature, for example. So, or select the most important features using principal component analysis, for example. So we need to select what is the most important features to play with instead of using the whole set of features, because some features are not important. Not all features have the same kind of variations or the same amount of knowledge. So we need to select the most important feature for us. So after working with data and after you are really ready for building your model, you go to model selection. I need to select a model to fit my data. And after training your model, and of course, we need to divide our data into a training set and the testing set. And now we are ready. I trained my model. Now we are in the testing phase. If you are testing your model, you can use something called confusion matrix. So the confusion matrix, it's a tool which is used for describing the performance of a classification model or a classifier on a set of test data for which the true values are known. So we have a test data. This test data, it's brand new data for our model, and I will use this test data for testing my model, right? Because I know it. I know how many classes. So we have some actual classes, and I will apply this data to my model, and I will get the predicted classes, and I will put those numbers into this table to check the performance of your model, if your model is good or bad. Because if you are training a model, you cannot just train your model and just, send it to your customer, for example. It will not work. You need to give him documentation of the accuracy of your model. We need to plot this confusion matrix. So this confusion matrix is very important, right? So imagine that someone he is, developing a system for Corona, and he asks people to make, analysis, for example. They take sample from people and analyze it, for example. So you need to test it. You heard a lot about systems which are not working, right? So it's very important to test the quality and the performance of your model. So how can we do this? We can do this with a confusion matrix. And this is very simple matrix. And this matrix, in fact, it maps the actual classes against predicted classes. And from this one, we can get some information about the accuracy of your model. We can get some knowledge about something called sensitivity, for example, precision, for example. So those numbers are very important. Type 1 error and type 2 error, those numbers are very important, especially when you are working in medical domain. So here we have in this axis, in y-axis, we have actual classes. In the x-axis, we have predicted classes. You can just arrange it as you want. We will do it now here for binary classification, but we can use it for iris dataset. Do you remember iris dataset in this handwritten digits? In handwritten digits, we have 10 classes, correct? So we can use it for any number of classes. But for simplicity in this example, we will do it for binary classification. For example, we have just decision yes and no, or positive and negative. So in the actual classes, you have number of cases which are positive, and it will be divided into, the model will be able to classify it, some part of it as positive, and some part of it will be misclassified as negative. So those positive cases, those positive who are classified as positive, we will call it true positive. And those positive cases which will be classified as negative, we will call it false negative, correct? Because it's positive, but we misclassify it as negative. So we call it false negative. We have some negative cases. Those negative cases, when it's correctly classified, we call it true negative. When it's some of it is misclassified as positive, we can call it false positive. It's false positive. Imagine you have a patient, and this patient has corona, for example, and he made a test. So maybe the system was able to classify him as positive. So in this case, we can just say he is true positive, which is positive. It's very good. So he is true positive, right? He has corona, and after taking a sample from him, the system said no, he is positive. So now he is positive. This is very good. You have another patient, for example, who is negative, but he has some mild symptoms. He has a kind of symptoms, and they feel worried, for example, and he decided to make analysis, for example. So they take a sample from him. He is negative, but the system said yes, he is negative, so he is true negative, right? Now he is safe, because he is negative and he was correctly classified as negative. So my system is very good. So in fact, our target here is to build a system which can maximize number of true positive and the number of true negative. This is very important. we need to maximize number of true positive and number of true negative. Or you can just say, we need to maximize all numbers which are located across this diagonal. Because here in this diagonal here, we have accuracy, right? We need to maximize accuracy because if the accuracy is 99%, it's much better than 85%. So we need to maximize accuracy. To maximize accuracy, you need to maximize true negative and true positive. So in fact, we need to maximize all numbers which are located across this diagonal. The other diagonal, in fact, it's a false positive and false negative. We try to minimize all false values, false positive and false negative. What does it mean, false positive? You have a patient. He is negative. He does not have any corona, right? But we made a test for him, and the system said no, he is positive. So in this case, we can say that he is false positive, right? He is false positive. He doesn't have corona, but the system said no, he has corona. And in this case, we will ask him to stay at home, for example, for 2 weeks, for example, right? Maybe he is, if he want to travel, for example, you can just say no, you cannot travel, you cannot be on board because you are positive. But in fact, it's false positive. So consequences will be nothing. In fact, he will just stay he will be the only one who will be impacted. He will stay at home for 2 weeks. Maybe he will take some medications, but it will not harm him, right? He will take some maybe antibiotics, maybe he will take some, he will be under observation, for example, but it's okay. So we call this one, it's type 1 error. We call it type 1 error. So he is negative, but he will be misclassified as positive. So we can just say he is false positive. But on the other side, if you have a patient who is positive and the system said, no, he is negative, right? He is positive, but the system classified him as negative. So in this case, he will be false negative. This is very dangerous. We call this one type 2 error. And imagine you have a patient, he is positive corona, but he made a test and the system said, no, he is negative. So he can be on board and he can fly. He can go to work. He can go to his classroom, right? He has corona, but he doesn't know that he has corona. He made a test and the system said he is negative, right? So this one, it's very dangerous. This type 2, it's very, very dangerous one, in fact. So when you are building a system for a medical application, for example, they will discuss a lot this kind of type 2 error, because this one is very, very important. Imagine you have a patient also, maybe he has kind of disease, for example, he has cancer, for example, but after making a blood analysis and stuff like this, they said, no, you are negative, you are okay, you just go home. And he will die after a few weeks, for example, because he didn't take the medications and the stuff like this. So this one, it's really very, very dangerous type 2 error. So if you are building a system for a hospital or something, you need to be careful about type 2 error. And if people are building systems very quickly without testing it, it's catastrophic because it might have very negative consequences, in fact. So accuracy will be a total positive plus total negative divided by total number of cases. And the precision, it's total positive divided by total positive plus false positive. So, we have all those numbers. We can get those numbers also from Python. I have here some example. It is a basic terms of confusion matrix. What does it mean true positive? What does it mean true negative, false positive, false negative? Prediction error. Prediction error, it's 1 minus accuracy. So if we are calculating the accuracy, once you have the accuracy, so the prediction error will be 1 minus accuracy. So if the accuracy is 0.9, it means the error will be 0.1, right? So true positive rate, false positive rate, precision, and recall. We can get all those numbers, in fact, from sklearn.metrics. So we have in this library, if we will use sklearn.metrics, we can get those numbers from sklearn. We can, we can get the confusion matrix, and we can get also all numbers from the confusion matrix. Yes, this is an example. You have, it might be an example. You have 165 patients, for example. It's a system for medical testing. It could be a system for testing a corona, for example, if the patient has a certain disease or not. We tested the system with 165 cases. So in the media, even when they are talking about the systems, they must test it. They must have enough time, in fact, for testing it, and they must test it with lots of people. And those people, they should come from different areas, different domains, different gender, different age, kids, old people, young people, healthy people, sick people. So this sample, in fact, it must. If you need to trust on those, because I can select a sample from healthy people. So I can build a system for testing corona, for example, and I can just go for people, I mean, from university, college, or university, and ask them to test my system. So all of them are healthy. Maybe they will get little symptoms, but they will recover quickly. So in this case, the sample is not representing, I mean, the whole population. If you want to test a system, and it's something in statistics, if you need to test your system, you need to select a sample which is covering the whole population. We cannot be selective here, right? If you need to build a system in China and use it in Norway, for example, it will not be possible because we don't know. I mean, the sample which they have been selecting in China, for example, it's not representing the whole population. So if you need to build, and that is why, for example, if you build a system in Norway, you cannot use it in US. They need to test it in US first before approving it. So it's very, very important because the sample which we are selecting, we cannot claim that this sample it's representing our population. We need to select it in random. There are many ways, in fact, in mathematics. How can you select the sample? So it should be in random, and it should covering all genders, and it should cover all ages, and also medical status and mental status and so on. So you need to get a sample which is representing the. So in this experiment, we have 165 patients, and we are testing them. 60 from them are negative, 105 are positive. So those are the actual, how do you call it? We call it actual class. So this is the actual class. This one, it is a predicted class. This one, it's predicted. Which means among those 60, 50 has been classified as from those 105, 100 was correctly classified as yes or positive, 5 was misclassified as negative. From those 60, which are negative, 50 were correctly classified as negative, and 10 was classified as positive. So this diagonal will be this time this one. So if you want to find the accuracy, it will be 50 plus 100 divided by 165. So this is the accuracy. So it will be 150 divided by 160. It will be the accuracy. If you want to find the prediction error will be 1 minus accuracy. And we can get from here precision, we can get recall. Those numbers are very important. Yes. So, you can just continue with the example. You will get the accuracy, you will get misclassification rate, true positive rate, false positive rate, true negative rate, precision, and so on. So those numbers are very important, in fact. So when you are building a system, so imagine you are working in your project, you are building a system for medical diagnosis in your bachelor project, you need to get all those numbers. And you need to discuss those numbers with someone from the domain. So if you are working with some doctors from the hospital, for example, or a researcher, after finishing your system, the task is not finished yet. You need to get all those numbers, and you need to discuss those numbers with one who is expert in this area. Yes. How can we get the confusion matrix for Iris? We need, we build a model already for Iris. We build many models, logistic regression, and so on. So how can we get this confusion matrix? We need to import confusion matrix. We need to import this confusion matrix, in fact, from sklearn.metric. So if we can go back here. Yes, maybe it's not here, but it's important to remember it because you will get an error message. So anyway, we build a model. We will use the test data. We need to generate this confusion matrix for the test set, right? So we need to we need to calculate the confusion matrix for actual classes against the predicted classes. So this one, it's actual, right? And this one for predicted. In this case, you will get this confusion matrix, and you can plot the confusion matrix. So from this confusion matrix, we have, I don't know why it's 50 plus 49. Maybe it should be 100. But anyway, we have 49 from class 0 correctly classified as 0. We have 50 from class 1 correctly classified as 1, right? I did it for all data set, in fact. In this example, we didn't divide the data into training and testing. So we are just doing it for the whole data set. So just to summarize, we have been working with this single layer neural network. Single layer, it's linear model. So single layer, we are working with those linear models, and it looks like this one. It could be a perceptron, it could be a linear adaptive unit, for example. It could be a regression model. All those kind of models are linear simple models because we have only one neuron. So when we represent this one, we have only this one. We have only one circle. It connected with some inputs, right? And that is it. So in fact, this one, it's one unit or single layer neural network. Now we need to start working with multi-layer neural network. This one, it's simple. It can be used for classifying only linearly separable data sets, right? It must be linearly separable. If it is inseparable, it will be impossible, right? You need to work, you need to tweak it, for example, and work with the features as we did before to make it linearly separable. Otherwise, this one will not be helpful for us. So, and this one is used for binary classification, only binary classification. So the output here will be just 0 and 1, correct? So this one, it's a very simple one. We train this one by minimizing this cost function. This cost function, it's mean squared error. So this one, it's mean squared error. And this is a law for updating the weights, omega equal omega plus delta omega. How can we find the delta omega? We find the delta omega using gradient descent. How can we do it using a gradient descent? So delta omega will be minus eta multiplied by partial g by partial omega. It's minus learning rate multiplied by gradient. This is the gradient. And in gradient descent, we move against the gradient. So therefore, we have this negative sign here, right? We have here minus. So this minus because all time we try to move against the gradient. So if we can plot this cost function like this one, it must be convex. Therefore, this one it's squared. When it's squared, it will be convex. Why it's convex? Because when it's convex function, we will be sure that we will reach the bottom at some point. So the idea here is to reach this one. There is a guarantee when it's convex function. There is a guarantee that we will reach the bottom here. So we're starting from some point here or there, and you move against the gradient. So if you are starting here, for example, so the gradient here is negative multiplied by negative, so it will be positive. So in this case, this is the direction of increasing x. And if you are here, for example, the gradient here, it's positive multiplied by negative, so you will move against it in the direction of decreasing y. So in this case, we will move in this direction until we reach this point. This point, it's x star, we call it x star. Or it's x, which will minimize this function g omega, or omega star, for example. So this is simply, I mean, and if you want to implement it, I mean, we implemented it before for the perceptron, for logistic regression, linear adaptive unit also, and it works fine. So single layer neural network, we can use it for binary classification. We can use it for linearly separable data sets. If it is inseparable, it will be impossible to use this one. We can use this one for multi-class classification. When it's multi-class classification, we will simply generate one for each class. We will get one for each class. And we use a technique called 1 over rest. 1 over rest. So it will deal with a class as the class which we are interested in, and the rest will be the rest. It will be 0. Yes. Next, we need to go to multi-layer neural network. So if we finish this single layered neural network, we need to go to multi-layer. Multi-layer, it's just simply, we have here, this one, imagine this one, it's a perceptron. So we're just connecting many of those perceptrons. So, and we will put in layers, we will make connections to make it more complex. That is it. So we have been working with only one unit. Now we have a data set which is really complex, and the perceptron will not able to help us for solving it. So in this case, we will start connecting, we will just put things together. We will have lots of those perceptrons connected together in layers. And so this one will be one hidden layer, for example, and we can have lots of those layers. So we can have many layers. This one, we call it output layer. So you can just add lots of layers, hidden layers, and those connections, there is no law for anything. You can just select any numbers. So you can select how many hidden layers and how many units in each layer. So here, we have here an input layer. The input layer, it's nothing, in fact. It's just transferring inputs to the second layer. Inputs are connected to the first hidden layer using those weights, as we know in perceptron. So if we need to calculate, the outputs from this layer, we need to multiply omega by input. So we will get omega x or omega transpose X, for example. And after that, we will apply it to the function. There's an activation function. I call it phi, for example. Now we have the output, right? Now we have the outputs. You will get the outputs here, multiply it by the next layer weights. Imagine it's V, for example. You will calculate new values here, apply it to the cost function, to the activation function here, and so on. So in fact, we go forward to calculate the output. And after calculating the output, we will calculate the error. So the error will be t minus 1, t minus 1. And we know that it's convex, so it will be squared half. And this is our cost function. So we will use, in fact, the same cost. We will use, in fact, the same cost function, right? We will use the same cost function, and we will go backward step by step using to adjust the weights. So we will calculate the error signal here, and after that we will go here to adjust. So we will calculate delta V. We will adjust the weights here, and after that we will go to the next layer, calculate delta omega, and so on. I mean, error backpropagation, I will make maybe next week. I will have more details, and also we will try to implement it for simple feed-forward neural network. Okay. So how backpropagation works? I mean, it works in two steps, many steps. In fact, we go forward to calculate the output, and after that we calculate the error signal, and we go backward for adjusting the weights. Yes. Just please let me know if you want to take a break or something. Should we just start using MLP and sklearn, and after that we can take a break, so you can just have an example to work with. I mean next week I will try to implement error backpropagation step by step. I will try to make it simple so we can understand the concept and how can we implement it. But in reality, if you are using Python or MATLAB, you don't need to use, you don't need to implement it by yourself, but we just need to implement it by ourselves to understand the concept behind it. So MLP in sklearn, MLP, it's for multi-layer perceptron. So do you see perceptron? We still have a perceptron, but we call it multi-layered perceptron. So we create multi-layers from those perceptrons. Why it's in layers? It's in layers because it will help us to make calculations much faster and much efficient. If you have some inputs here, for example, we have a vector here, which is X. We have weights here. So this one will be a matrix. This matrix will be 3 times 4, right? Because we have 3 inputs connected to 4 units or neurons. So this weight matrix here, or the connections here, it will be 3 times 4. We have bias also. So the bias will be 1 times 4, for example, right? If the width here is omega, if the width here is V, for example, what will be the size here? So in this case, V will be a matrix 4 times 4. If the width here it's U, for example, so it will be matrix 1, 2, 3, 4 times 2. So it will be 4 times 2. So in fact, when we structure feed-forward neural network into layers, it makes calculations very easy for us because we can use matrix notations to make calculations more much faster. So if I want to calculate the inputs to those weights, it will be omega times X. So we will get some values here. You can just call it O, for example. If you multiply it O by V, we will get the outputs here, right? And so on. So so calculations, when we structure it as layers like this, it will make calculations much easy to deal with. We will go forward for calculating the output, and once we have the output here, we can subtract it from the target value, so we can calculate the error signal, and then we will go backwards. When we go backward, we will differentiate this function using a chain rule, and we will adjust the weights for this layer first, and after that for this layer, and finally for this layer. So we'll do it layer by layer. So in MLP, in sklearn, in fact, we have this. We will go back to this. Logistic regression. I mean, we imported, in fact, logistic regression from sklearn.linear model. Do you see? And we have been working with logistic regression, for example. Logistic regression, it's a kind of linear model. So in fact, we import logistic regression from sklearn.linear model, right? We import this one from linear model. But in case of MLP, we will import it from neural network. So if you want to import MLP classifier, we call it MLP classifier. We will import it from sklearn.neural network. So now it's a neural network. And a neural network, it consists of layers. The first one, it's the input layer. The last one, it's the output layer. And in the middle, we can have a number of hidden layers. All those layers consist of number of neurons, and all those neurons are connected with each other by connections. And each connection has a weight value, right? And means this weight value, it will represent the importance of the signal or the input value, for example. It could be large value, it could be small value. And it's according to the problem, because maybe this feature is important for solving the problem. So in this case, the weight value will go up or go down, right? So the neural network or the optimizer will decide this. So if you want to use MLP classifier from sklearn, we need to import it from neural network, sklearn.neural network. It will be MLP classifier. And once we have this MLP classifier, we will just adjust, we will select, we will decide the activation function, how many hidden layers, how many units in each hidden layer, and so on. As we mentioned before, I mean, the pipeline for machine learning, we need to start with the data. So first, we need to upload our data. So now I'm uploading my data. I just selected all X and the whole Y, because now I know Iris data has 4 inputs and 3 classes. So I will just select all data, because now I'm working with multi-layer perceptron. Multi-layer perceptron, of course, it will be more capable than perceptron. It's important to remember to divide your data into a training set and a testing set, right? So we need to divide the data. We can use a function called train test split. How can we get this function? We can get this function also from sklearn.model selection. So train test split, we can import it from sklearn.model selection. So the input to this function will be X and Y, because we need to divide X and Y into a training set and a testing set. This function, it will shuffle the data set before, because as you know, in Iris dataset, it consists of 3 blocks. So the first 50 data points, it's for class 0. The next 50 data points, it's for class number 1. The third 50 points are for class number 2. So in fact, it's not shuffled, right? So if you want to split it, you need to shuffle those data sets. Why we need to shuffle it? We need to shuffle it to be sure that all classes are equally represented in each set. We will have a training set and a testing set. So I need all classes to be represented equally, in fact. How can we do this? So first we will shuffle. Shuffle will be done automatically here. So in the back end here, shuffle will be done automatically. You don't need to shuffle it, in fact. But you need to use this stratify, right? When we use stratify equal y, we will be sure that, I mean, the 3 classes will be equally represented in the training set and in the testing set. Now we will train the model. In the model here, it's MLP classifier, right? We need to select the optimizer or the solver. This is the solver. It's SGD. I selected SGD, and the SGD means stochastic gradient descent. So this is a learning approach. So we will use a stochastic gradient descent to adjust the weights of this model. I mean, random state, you need to select this one if you want to generate or initialize your model using the same values, or for the same region, for example, random values for reproducibility if you want to reproduce your system later on. This is the hidden layer size. I put 5. I mean, when you select, I mean, this one, it's in fact, it means we have only one hidden layer. This one means we have only one hidden layer, and this hidden layer has 5 neurons. Maximum number of iterations. So this is the maximum number of iterations. This alpha value, it's something about L2 regularization technique. We will talk about it later on. But if I want to plot this model, in fact, so we have only one hidden layer, so I will plot it. And this hidden layer, it has 5 units or 5 perceptrons. So I will plot it. 1, 2, 3, 4, 5. So this is my hidden layer. It has 5 neurons. How many outputs here? Right? I mean, we will use the data for training the model. So in fact, in this model, we don't need to specify the number of inputs and number of outputs. The model will understand it from this model dot fit. So we have here 3 classes. So we should have 3 outputs, correct? So we will have one class for Setosa, for example, one for versicolor, one for Virginica. We have 3 classes. How many inputs in my data set? In fact, in my data set, we have 4 inputs. We have 4 features. So I will make small dot because this is the input layer. The input layer, it's just nothing. It's just connecting inputs to the hidden layer. So we have here X1, I will call it X1, X2, X3, and X4. Make all those connections, right? It's connectionist. So we just make all those connections. Make all those connections. Connect all inputs with weights, with the inputs to. Okay, now we make all connections. And it's the same also, connecting the hidden layer with the output layer. So this one will be connected like this one, right? So just make all connections. So now this is my neural network. Do you see? So if the weights here called omega, weights here called V, for example, I can call this one omega 1, 1, right? This one is omega 2, 1, omega 2, 1, 1, 2, 1, 3, 1, 4, and so on. So in fact, this one, it will be a matrix. The size of this matrix will be 4 times 5. Correct? This one, it will be 4 times 5. V, what is the size of V? V, it will be 5 times 3. Right? So this is the amount of weights. So how many parameters here compared to a perceptron? I mean, we solved this problem exactly using a perceptron. And a perceptron, we used maybe 4 inputs, or 2 inputs, for example. I mean, we used it for multi-class classification. So if you want to find number of parameters here, so this one, it's 4 times 5. 4 times 5, which means 20. Right? So it's 20 weights. We have here 15 weights. Plus, how many bias here? It's 3. How many bias values here? It's 5. So in total, it will be 25 plus 18. 25 plus 18. So it will be 43 weights. So do you see? So the model now has more capacity, in fact. The model now has more capacity. When it has more capacity, it has better capability to learn systems, map inputs into outputs. So this model should more capable, in fact, than a perceptron. This one will be class, we call it 0, 1, 2, for example. So this one will be class, which is Setosa, Versicolor, and Virginica, right? So I just call it 0, 1, and 2, right?
So is question.
Yeah.
Is it a general rule that the more total weights and biases a system has, the more flexible it is?
No, it will has more capacity, in fact, to map it. Yeah, it will. Yes, I agree with you, but we need to be careful because when number of parameters increases, you need more data to train your model, right? And if you, if you selected many hidden layers and many neurons, so maybe this number will increase a lot. And in this case, maybe your data set will be too small to adjust all those weight values. Right? So maybe your system will have underfitting problem. Underfitting, it means my model, or it could be underfitting or overfitting, right? So I don't have enough data to train my model, right? Or maybe my model is too complex and it's too tough. So he just memorized the data quickly. He memorized it, not training it, not fitting it, but memorizing it. So we call it overfitting. But when number of weights increases, of course, the model will be more capable for solving more complex problems. So in deep learning, for example, I mean, those number, this one, it's a shallow learning. Number of weights here, it's 43 parameters. But when you go to deep learning, for example, you will have millions of weights. So maybe you can have a simple one for machine vision, which has 20 million or 40 or 50 million weights. So it will be very, very complex. And therefore, in deep learning, in fact, we need more data to train the model. Why? Because the system is very complex and it has lots of weights, and we need to have enough data to train the model. So it will take more time for training, and also it will require more data for training your model. So and when we used this model we just used this model for training we used the XTrain Y-train, and now we are doing it for X-test. We calculate the prediction error, for example, and after that we can plot the confusion matrix. When we have the confusion matrix, we have the confusion matrix here for the training and testing. And if you can see here, it's only 3 cases here in the training. Do you see this one? So in fact, it's a 3 from class 1 has been misclassified as 2. So we have only this problem here in 3 classes. But when we go for the testing accuracy, it's 100%. So the accuracy here, it's 100%. Right. Because here we have 40 from class 0 classified as 0, 37 from the 40 of class 1 classified as 1, and the 3 from class 1 misclassified as 2. So this one, it's wrongly classified, in fact. So maybe the accuracy here will be like 97%, for example, but for the testing data set, it was 100%. So I just did it I want you now. We will take break. We will take, for example, 15 minutes break. But please go to this MLB sklearn and try to run it one more time and try to make some changes. So try to make some changes to the model. For example, try to change this one, for example. You can change a number of hidden layers. You can try to plot the training the loss function, for example, for training and testing, for example. So try to make some changes, and we will meet after 15 minutes. So we can meet 11:30, for example. Is it fine? Yes, I cannot see the chat window. Okay, no problem. So we will meet after 15 minutes at 11:30, and please during those 15 minutes drink your coffee and try to go to the code in this GitHub MLB_sklearn, and try to run this one more time and try to make some changes. Yeah, and see you after 15 minutes. Thank you very much.